Introducing the CelluCov biodegradable lateral flow assay is a proof of concept for eco-friendlier point-of-care testing.
At-home diagnostic tests have reduced burns on the healthcare system. 97% of plastic residues from these tests are currently incinerated, releasing greenhouse gases. Additionally, increase in test manufacturing does not correlate with an increase in affordability or usage of the test for low-income population. The CelluCov team has created a testing kit that maintains functionality of current test kit using materials that can break down within 6 months of being placed in landfill or septic environments. While the test was originally designed to be disposed of in septic tanks globally, its affordable and eco-friendly design can provide many benefits within the United States as well.
Current testing kits use about 10 grams of single-use plastic, which does not degrade. The CelluCov kit instead uses 3D printed polyhydroxybutyrate or PHB plastic for the test cassette, as well as the buffer vial caps and bottom. The body of the buffer vial is made from polyhydroxyalkanoate or PHA plastic straws. These plastics are produced from bacteria and kept to degrade completely within 6 months from being consumed by the bacteria found in soil and water. The instruction manual is made from a paper which dissolves in water with its text printed in algae-produced ink. The nasal swab is made from a cotton swab and paper stick, and a nano-charcoal desiccant is placed in a paper bag to reduce moisture in our kit. The polyvinyl bags provide extra protection for the nasal swab and test device. Finally, a test is composed of a sample pad made of cellulose filter paper, conjugate release pad made of compostable paper coffee filters, a test strip made of cellulose filter paper, and finally, an absorbent pad made of bamboo toilet paper. These materials can replace the fiberglass and cellulose components, which take longer to decompose.
Initial tensile testing on the device reveal a lower Young modulus for the PHB filament than the Young's modulus of polypropylene cited in literature, which is the primary plastic used in COVID tests. This lower brittleness demonstrates the reduced risk of the CelluCov test breaking into microplastics that could harm wildlife as compared to the current tests thrown into landfills. A decrease of 1 milligram per liter squared in dissolved oxygen concentration in water containing only septic bacteria in our filament additionally serves as evidence of preliminary degradation by these bacteria for nutrients. Finally, we have seen degradation of PHB beginning on the surface with statistical significance between a control and river plus septic concentrations of 8 grams per milliliter. Additional significance can also be seen between bacteria and all other degradation groups. Our conjugate release pad was treated, and a running buffer placed on the conjugate release pad carried the nanoparticles to the absorbent pad, demonstrating that our test could carry golden nanoparticles to properly function as a lateral flow assay. From using common affordable materials to the familiar design to aid in user friendliness and minimize medical mistrust with new users, we believe the CelluCov test will be successful in combating both pollution and providing healthcare to all.